Welcome to the deep dive. Today, we're tackling logic, really, the foundation of clear thinking.
That's right. It's fundamental.
You know how we always try to dig through all the information, find those crucial insights, the surprising bits, the aha moments that actually stick? That's exactly what we want to do with logic today. We've looked at, well, everything from academic texts to online resources like the Wikipedia entry.
Yeah, the goal is to cut through the complexity.
And give you a really solid grasp of this essential field.
Exactly. We want to show what logic really is, looking at, both the structured, formal side and how it actually works in everyday arguments.
Because it's not just for philosophers, is it?
Oh, definitely not. Understanding logic is relevant everywhere in coding, making decisions, just navigating the information overload we all face.
Okay, let's start to unpack this then. At its heart, logic is, well, it's about figuring out what makes sense,
Yeah,
right?
it's a good starting point.
We'll explore formal logic first, maybe. That sounds like the mathematical backbone.
It is, in a way. It deals with arguments where, look, if the starting points of the premises are true, the conclusion has to be true. It's purely based on the argument's form.
Like a kind of geometry of thought.
That's a neat way to put it. And then there's informal logic.
Right, that sounds more like real life.
Exactly. That's about how we actually argue, in normal, sometimes messy human language.
Okay.
That's where we look at things like misleading arguments, fallacies, and just critical thinking skills in general.
And you mentioned a logic can also mean something specific.
Yeah, just to add a layer, a logic can refer to a specific formal system, one with its own particular set of rules for proving things.
Interesting. So many layers already.
But what's fascinating is that all these sides of logic are really about analyzing arguments.
And an argument in logic isn't like yelling at each other.
No, definitely not. It's a structured set of statements. You have premises.
Oh, your points.
Right, the premises.
Yeah.
And they're intended to lead you logically to a conclusion. And these premises, the conclusion, they're propositions. Statements that can be either true or false.
And these propositions themselves have an inner life. Is that what you said?
Sort of, yeah. They have an internal structure, whether they're simple claims like the sky is blue or more complex ideas built up from simpler ones. We'll get into that.
So where did this whole idea even start? What's the origin story here?
Well, the word logic itself comes from the ancient Greek logos, which is just an incredibly rich word.
I've heard that. It means more than just logic, right?
But much more. Reason, yes, but also discourse, language, even the underlying order of things. Traditionally, logic was defined as the study of the laws of thought, or correct reasoning.
Correct reasoning.
Usually framed in terms of inferences, the mental act of drawing a conclusion, or arguments, which are how we express those inferences out loud.
Okay. So inference is the internal jump. The argument is showing your work.
Precisely. An argument, logically speaking, is just those premises offered up to support a particular conclusion. And the big question logic always asks is, does that support actually hold up? Do the premises genuinely lead to the conclusion?
And that question connects formal and informal logic.
It does. That's the shared goal, even if the methods are different. Though, historically, formal logic has often been seen as the main thing. Some logicians even equate logic entirely with that symbolic approach.
Okay, let's get into that then. Formal logic. What makes it formal? It does sound a bit imposing.
Think of it like taking an X-ray of an argument. Formal logic, or symbolic logic, uses symbols to strip away the specific topic.
Right.
So you can see the underlying logical structure, the skeleton. That's why it's so crucial in mathematical logic.
Because it doesn't matter if you're talking about apples or oranges, it's the pattern.
Exactly. It becomes topic neutral. The validity depends on the pattern, the form, not what it's about.
So instead of saying, if it rains, the street gets wet, you'd use symbols, like P and Q.
Precisely. If P, then Q. Formal logic is really focused on deductively valid arguments.
Deductively valid. Okay.
In these arguments, if the premises are true, the conclusion must be true. There's just no other possibility.
Yeah.
It's impossible for the premises to be true and the conclusion false.
Guaranteed.
Guaranteed by the form. This certainty comes from following specific rules of inference. Patterns of argument structure.
Can you give an example?
Sure. The classic one is modus ponens. It goes, premise 1, P is true. Premise 2, if P, then Q is true. Conclusion. Therefore, Q must be true.
Okay.
And that structure works no matter what P and Q actually stand for. It's a guaranteed logical link.
So it's all about these unbreakable logical chains based purely on the shape of the argument.
That's a really central idea, yes. Now, there's another way to think about formal logic, too,
Oh,
as the study of logical truth.
logical truth.
Yeah, a proposition is logically true if its truth depends only on the logical words it uses, like and or not, if, then.
Uh-huh.
It's true in absolutely every possible scenario, regardless of what the non-logical parts mean. Think of either the door is open or the door is not open.
Right, that has to be true.
Exactly. It's true no matter what door we're talking about.
Yeah.
And these two concepts, deductive validity and logical truth, they're tightly linked. If an argument going from P to Q is deductively valid, then the statement, if P then Q, will itself be a logical truth.
Okay, that makes sense, but it still feels very abstract. How do we actually use this for a real argument someone makes?
Well, that's where translation comes in. You have to take the argument, which is usually in natural language like English, and translate it into a formal language, something like first-order logic. These languages have a very strict, limited vocabulary and precise rules, a syntax for how you build formulas.
Formulas, like logical sentences.
Exactly. Well-formed formulas. For example, Carmen is Mexican, and a teacher might become, say, MC.
Okay, so C is Carmen, M is Mexican, T is a teacher, and the wedge thing means and.
You got it. That's the and connective, yes.
Yeah.
It's like rebuilding the sentence with logical Lego bricks, as you said earlier.
Right. I like that analogy.
Once it's in that formal structure, then you can apply the precise rules of inference to check its validity.
So you can't just analyze my rant from yesterday directly with formal logic.
Probably not directly. You'd need that translation step first. And this leads to the idea that there isn't just one logic.
But many. You said a logic.
Exactly. A logic, technically, refers to a specific formal system. Different systems might accept different rules of inference or use slightly different formal languages.
So there are different brands of logic systems.
Kind of. Since the late 1800s, there's been a real proliferation, a big increase in these different formal systems. And funnily enough, logicians still debate what actually qualifies as a logic.
They argue about logic itself.
Sometimes, yes. For instance, some argue only systems that are logically complete, meaning they can prove all the logical truths expressible within them, like first-order logic should really count. Which raises questions about other systems, like higher-order logics.
That's brilliant. Okay, so if formal logic is about these precise abstract systems, let's switch to informal logic. That sounds like where the real-world messiness comes in.
You absolutely nailed it. Informal logic steps back from the symbols and looks at how we actually argue in everyday language.
Because formal logic struggles with that sometimes.
It can, yeah. Formal structures often have a hard time capturing all the nuances, the ambiguities, the context dependence of natural language arguments. Informal logic grew partly out of that difficulty.
Right.
It tackles issues formal logic might miss, but the core goal, it's still the same.
Assessing arguments, seeing if they're good or bad.
Exactly.
Yeah.
And identifying fallacies, those common reasoning errors.
So formal logic is the ideal playbook, maybe, and informal logic is watching the actual game, spotting fouls.
That's a really good way to think about it.
Yeah.
Now, finding one single precise definition for informal logic is tricky. It's more of a field with several overlapping ideas.
Okay.
One view is pretty straightforward. It just studies arguments as they appear in natural language, English, French, whatever.
Sure. As opposed to the formal translations.
Right. Formal logic analyzes the translations.
Yeah.
So an argument like, birds fly, Tweety is a bird, therefore Tweety flies. That's informal logic territory because it's just plain language.
Even though Tweety might be a penguin.
Exactly. That's a problem formal logic might not see easily, but informal logic dealing with content might pick up on. That's the challenge of natural language.
Ambiguity, vagueness.
Context dependence, all that. Now, a broader view sees informal logic as studying the standards of good argumentation itself. Rationality, critical thinking, even the psychology behind how we argue.
So not just the sentences, but does the argument actually make sense in the real world considering everything?
Precisely. Does it hold up?
Okay.
Then there's another perspective. Informal logic focuses on non-deductive arguments.
The ones that aren't guaranteed.
Right. Where the premises make the conclusion likely but not certain, unlike the absolute certainty aimed for informal deduction.
Like seeing loads of white swans and concluding all swans are white.
Perfect example. That's an inductive argument, a type of non-deductive reasoning often studied in informal logic.
So it's about plausible conclusions, even if we might be wrong sometimes.
Exactly. And one more view defines informal logic mainly as the study of informal fallacies.
The errors in reasoning.
Yeah, The ones that stem from the content or the context, not just the logical form, like attacking the person instead of their argument, the ad hominem fallacy.
Right.
And finally, some see it as formal logic deals with general patterns, informal looks at specific examples. So yeah, it's a diverse field.
It definitely sounds like it's trying to make good reasoning practical for the arguments we actually face every day.
That sums it up very well. Okay, shall we move on to some of the basic building blocks, concepts that apply across the board?
Yes, let's get down to the fundamentals. What are the absolute key pieces?
Right at the core, you always have premises and conclusions. We've mentioned them a few times.
The start and the end point.
Exactly. And in a good argument, the premises provide support for that conclusion, like elephants are mammals and mammals are warm-blooded. Support. Elephants are warm-blooded.
Okay.
Now, these premises and conclusions, they are what we call truth bearers. They can be true or they can be false.
Makes sense.
In modern philosophy, the main view is that these truth bearers are either propositions, the abstract meaning behind a sentence, or maybe the sentences themselves, the actual words.
So the idea versus the specific wording, is there a difference?
Well, it matters philosophically. Focusing on propositions raises questions about these abstract meanings.
Yeah.
Focusing on sentences runs into problems with, say, ambiguous words or context. It's an ongoing discussion.
What about thoughts? Could they be premises?
That was an older idea called psychologism, seeing them as mental states. But it's not really the mainstream view today.
Okay, so arguments are built from these true-false units. What about inside them? Are they always simple?
No, they can be simple or complex. A complex proposition is built by linking simpler ones with logical connectives.
Like and, or, if, then.
Exactly those. A simple proposition doesn't have other propositions inside it, but it still has its own structure. It has parts like singular terms, that specific cat, and predicates is black.
Got it.
Now, the truth of a complex proposition, if it uses what we call truth-functional connectives, depends entirely on whether its simpler parts are true or false.
Okay.
For simple propositions like that cat is black, its truth depends on whether the term that cat and the predicate is black actually match up with reality. That's studied in theories of reference.
So the apple is red is true if the thing I'm calling the apple really is red.
Precisely. Now here's where it gets really neat. Some complex propositions are true no matter what.
Regardless of the parts.
Yes. In classical logic, something like either it is raining or it is not raining is always true. That's a logical truth.
Because it covers all possibilities.
Its truth depends only on the logical words, either or not. It holds true no matter how you interpret raining. Some philosophers even define logic itself as the study of these logical truths.
Statements that are true just by their structure.
You're definitely on the right track. And a fantastic tool for seeing how this works, how connectives function, is the truth table.
Ah, the grids with all the T's and F's. I remember those.
That's the one. Truth tables map it all out. Columns for the simple propositions, rows for every possible combination of true, false, often TF or 10.
Right.
And the table shows the resulting truth value for the complex proposition in each case. Like P and Q is only true in the one row where both P and Q are T.
Okay.
You can make tables for all the main connectives, not if, then, even less common ones. And you can build them for really complicated logical statements too.
So it's a visual way to check all the logical outcomes.
Exactly. A very powerful visual tool. And we've used arguments and inferences a lot.
Yeah, are they different?
Technically, yes, though often used interchangeably in logic talk. An argument is the set, premises plus conclusion. An inference is the actual process of reasoning, the mental leap from premises to conclusion. Arguments are judged correct or incorrect based on the support. Premises and conclusions are judged true or false based on reality.
Got it.
And in formal logic, there's the idea of a sound argument.
Sound.
It means the argument is logically correct, valid, and all its premises are actually true.
So a valid argument structure isn't enough for soundness. The starting points have to be true too.
Exactly right. Now, arguments can be simple, or they can be complex chains. You know, the conclusion of one step becomes a premise for the next.
Like building a case piece by piece.
Right. And for the whole chain to work, every single link has to be strong. And this strength of support varies. Deductive reasoning gives the strongest possible support.
The guaranteed kind.
Yes. Then you have ampliative or inductive reasoning, which offers weaker but still valuable support. Deduction is closely tied to formal logic. Ampliative reasoning often falls under informal logic.
Okay, let's dive deeper into those two. Deductive versus ampliative. What's the core difference again?
Okay, deductive validity. We touched on this. If the premises are true, the conclusion cannot be false.
Guaranteed.
Think, all squares are rectangles. This shape is a square. Therefore, this shape is a rectangle. If premises 1 and 2 are true, 3 must be.
Okay.
And crucially, validity is about this necessary link, not whether the statements are actually true about the world. An argument can be valid even with false premises.
Like the flying cats example.
Exactly. All cats can fly. Tweety is a cat, therefore Tweety can fly. The form is valid, even though the first premise is obviously false. The logic holds.
So deductive arguments are all about that airtight connection.
Precisely. Alfred Tarski, a famous logician, highlighted key features. They're formal, depend on form, a priori, don't need experience to verify the link, and modal, hold by logical necessity.
Right.
This formality connects to rules of inference, like modus ponens. If an argument structure follows these rules, it's valid. If not, it's invalid.
Right.
And deductive inferences are truth-preserving. True premises always lead to a true conclusion.
Does deduction actually tell us anything new, though, if the conclusion is sort of already in the premises?
That's a classic philosophical debate. In one sense, no deep new information is added. But deduction can make surface information, stuff that was implicit, explicit. Think of complex math proofs. The conclusion wasn't obvious, but it was logically contained in the axioms all along.
Okay, I see. So that's deductive certainty based on form. What about ampliative arguments? They amplify knowledge.
Exactly. Ampliative arguments are where the conclusion genuinely goes beyond the information given in the premises. This is where we often get new insights or knowledge.
But there's a catch, right?
There is. The premises make the conclusion probable, maybe even highly probable, but they don't guarantee it. It's possible for the premises to be true and the conclusion false.
So it's not guaranteed.
No. And this means knowledge from ampliative reasoning is often provisional. We might need to revise our conclusions based on new evidence. This happens all the time in science and everyday life.
Right.
Unlike deductive arguments, valid and invalid, ampliative arguments are judged on a scale strong or weak support. The line can be a bit blurrier.
So it's about making the most reasonable guess based on the evidence, but accepting you might be wrong.
That's a great way to put it. Now, terminology can be tricky here. Sometimes induction is used broadly for all non-deductive reasoning,
Okay.
but often induction is seen more narrowly as one type of ampliative argument alongside abduction.
So what's induction in the narrow sense?
Usually it means statistical generalization. You've observed a pattern in many cases.
Like the black ravens?
Exactly. Say
Yeah.
thousands of black ravens, inductively conclude all ravens are black, or using a pattern to predict the next case. Every swan I've seen is white, so the next one probably will be too. Some philosophers stress that pure induction relies only on statistics.
Okay, and abduction, that's the Sherlock Holmes one, right? Inference to the best explanation.
Precisely. Abduction looks at evidence and asks, well, what's the best explanation for this being true?
Like the half-eaten sandwich on the desk example.
Yes. You see the sandwich, you infer the best explanation might be someone was here late working and got hungry. That conclusion explains the evidence.
But it has to be the best explanation available.
Crucially, yes. Well, they're just likely. There could be other explanations. Maybe a raccoon got in, but the late-night worker might seem more plausible. The best fit for the facts.
Got it. Deductive, certainty, inform. Ampliative, new info, but probable. That's a really key distinction. So what about when arguments mess up? Fallacies.
You got it. Fallacies are arguments that fail to meet the standards of good reasoning.
It's not just about the conclusion being false.
No, crucially, it's about the reasoning being flawed. You could have true premises and even a true conclusion, but if the logical link is bad, it's fallacious, like the grass is green, therefore the earth is round. Both true, but the therefore is nonsense.
Right.
John Stuart Mill added an interesting point. He thought a true fallacy needs to appear correct on the surface. That's why they're persuasive, why people fall for them.
So they're like logical illusions tripping us.
That's a good way to think about it. Now, fallacies are usually split into two big types, formal and informal.
Formal fallacies are about the structure again.
Yes, an error in the logical form, like denying the antecedent. If P, then Q, not P, therefore not Q. That pattern is always invalid, no matter what P and Q are.
Okay.
But most fallacies we encounter daily are informal. The error is in the content or the context.
And there are loads of these.
Yeah, tons. They're often categorized into fallacies of ambiguity, unclear language, presumption, dodgy assumptions, or relevance. Premises just don't connect to the conclusion. We could spend hours just listing them.
Maybe another time. So we have rules for good reasoning. Fallacies break them. Are there different kinds of rules logicians think about?
Yes, there's often a distinction made between definitory rules and strategic rules.
Definitory and strategic.
Definitory rules are the basic rules of inference, especially in formal logic. They define what counts as a valid step. Fallacies violate these.
Like the rules of how chess pieces move.
Exactly. Strategic rules are more like chess strategy. They're about how to use the valid moves effectively to reach your goal, to construct a strong argument, to prove your point.
Ah, knowing the rules versus knowing how to play well.
Precisely. Some argue logicians should focus more on strategic rules to help people reason better in practice, not just spot errors.
That makes sense. Okay, we keep mentioning formal systems. What exactly makes up a formal system of logic?
Right. Think of a formal system as a carefully constructed logical mini-world. It typically has three parts: a formal language, axioms, and a proof system.
Language, axioms, proof system.
The formal language has an alphabet, basic symbols, and strict grammar rules, syntax, for building well-formed formulas, the sentences of the system.
Okay.
The axioms are starting points, statements accepted as true within the system without needing proof.
Like fundamental assumptions.
Exactly.
Yeah.
And the proof system gives you rules of inference to derive new formulas, conclusions, from axioms or other derived formulas. Some systems also include semantics rules for interpreting the symbols, often assigning truth values.
So you build this self-contained logical universe, starting with basic truths and using rules to find new ones inside it.
That's a great description. And the proof system's rules are purely syntactic. They work based on the shape of the formulas, not their meaning.
Like symbol manipulation.
Right. A rule might say, if you have P and Q, you can infer P. You apply these rules step by step to build formal proofs. There are different styles, like natural deduction or sequent calculi.
And the semantics adds the meaning back in.
Yes, it connects the language to interpretations, often truth values. Semantic entailment means a conclusion is true whenever its premises are true in that interpretation.
How do we know if a formal system is any good? What makes it work well?
Two crucial properties are soundness and completeness.
Soundness and completeness.
A system is sound if its proof system never lets you prove something that isn't semantically entailed. Basically, you can't prove falsehoods relative to its own semantics.
Okay, so it doesn't lead you astray.
Right. And completeness is the flip side. The proof system can derive everything that is semantically entailed. You can prove all the truths within the system's scope.
So sounding complete means provability and truth line up perfectly within the system.
Exactly. That's often the ideal. Now, shall we look at some of the actual systems of logic that people have developed over time?
Yes, definitely. Let's explore the different types.
Okay. For, over 2 millennia, Aristotelian logic was basically logic in the West. But modern times have seen a huge expansion.
Right.
We can roughly categorize modern systems into classical logic, extended logics, and deviant logics.
Let's start with the big one, Aristotle. What was his main focus?
Aristotelian logic, though broad, is most famous for term logic, or syllogistics.
Syllogisms. I've heard of those.
Right. A syllogism is a specific argument structure. 2 premises, 1 conclusion. Each proposition has a subject, a predicate, and a copula, usually is or are.
Like Socrates is wise.
Perfect example. Socrates is the subject term. Wise is the predicate term.
Mm.
Unlike modern propositional logic, it doesn't focus on connecting whole propositions with and or.
It's more about how categories relate, like men and mortal.
Exactly. The famous square of opposition visually shows relationships between basic types of categorical statements. All S are P, no S are P, some S are P, some S are not P. Subjects could be universal, all dogs, particular, some dogs, indefinite, a dog, or singular Fido. But it mainly dealt with simple properties, is brown, and struggled with relations, is bigger than.
Okay.
Syllogisms link premises and conclusion via a shared middle term. A huge part of Aristotle's work was classifying which syllogistic forms are valid and which aren't.
Based on the pattern of subjects, predicates, and quantifiers like all or some.
Precisely. Valid. All mammals are animals, all dogs are mammals, therefore all dogs are animals.
Yeah.
Invalid. All dogs are animals, some animals are cats, therefore some dogs are cats. The form doesn't work in the second one.
Got it. That provides the historical base. How does classical logic compare?
Okay, classical logic is distinct from Aristotelian. It mainly means propositional logic and first-order logic.
The modern foundation.
Pretty much. It's classical because it relies on widely shared logical intuitions. Law of excluded middle, T or F, double negation, not P is P, principle of explosion, contradiction implies anything. Bivalence, exactly one truth value.
Right.
It was initially geared towards math arguments, but it's used more broadly now. Still, its core focus means it lacks built-in ways to talk about things like necessity, obligation, time concepts, often handled by extended logics.
So classical logic is powerful, but maybe needs add-ons for some philosophical topic.
Exactly. Let's look at its two main parts. Propositional logic uses atomic propositions, PQR, and connects them with and, or, if, then, etc.
Like PQQ.
Right. It treats whole propositions as basic units. It's great for showing relationships based on how complex statements are built, but it can't analyze inferences based on the internal structure of those propositions.
So it can't handle the logic inside all dogs bark.
Correct. For that, you need first-order logic. It includes all the propositional connectives, but also lets you talk about subjects, predicates, and quantifiers, some and all.
Ah, so you can break down the statements.
Yes. This raven is black, might be BR. Some things are black, could be BRSAX. First-order logic has rules for reasoning with these quantifiers and predicates.
That sounds much more expressive for talking about the world.
It is. Very powerful. Now, building on that, we have extended logics.
The add-ons you mentioned.
Exactly. They accept classical logic's core, but add new symbols and rules to reason about other areas, metaphysics, ethics, knowledge.
Like what?
Modal logic is a major one. It adds symbols for possibility, diamond, and necessity. Box.
So you can say it is possible that P, or it is necessary that P.
Precisely. Means possibly P, or P means necessarily P. And it adds new inference rules, like if something is necessary, it must also be possible.
Okay.
And they're different flavors. Deontic logic for obligation, permission, and ethics. Temporal logic for time. Epistemic logic for knowledge, belief.
Wow, that opens up a lot of formal reasoning possibilities for philosophy.
It really does. Another type of extension is higher order logic.
How does that extend classical logic?
Instead of adding new operators, it allows quantification over predicates themselves, not just individuals.
So you can say there exists a property.
Exactly. Like, there exists some property F, such that Socrates has F. This gives huge expressive power, especially in math. But it comes with tricky metalogical baggage, so first-order logic often remains the standard.
Powerful but complex. Okay, now for the rebels. Deviant logics. What makes them deviant?
They reject one or more of those core classical intuitions we mentioned earlier. They're seen as rivals, proposing alternative ways to reason.
Okay, give us some examples. Who's deviating and how?
Intuitionistic logic is a big one. It uses the same symbols but ditches rules like double negation elimination, not P doesn't automatically equal P, and the law of excluded middle. P or not P isn't always accepted as true.
Why reject those?
It's often based on a view of truth as requiring constructive proof. You can't just assume something is true because assuming it's false leads to a contradiction. You need to build it. It's important in constructed mathematics.
So truth requires positive evidence, not just lack of negative evidence. That's a fundamental shift.
It is. Then you have multi-valued logics. They reject bivalence, the idea of only two truth values, true, false.
So more options.
Yes. Ternary logics might add an indeterminate value, useful in linguistics for vague statements. Fuzzy logics go even further, allowing infinite degrees of truth between 0 false and 1 true.
For dealing with fuzziness, like sort of tall.
Exactly. And finally, paraconsistent logics. These are designed to handle contradictions without exploding.
Exploding.
In classical logic, if you have a contradiction, P and not P, you can logically derive absolutely anything, the principle of explosion. Paraconsistent logics block that inference. They're motivated sometimes by dialetheism, the idea that some contradictions might actually be true.
Wow. So deviant logics really question the absolute bedrock of classical thought. That's mind-bending. Now, what about informal logic? Can it be seen as a system too?
Well, it's generally less about building formal systems. It's more focused on analyzing real arguments, fallacies, specific contexts. But some frameworks do try to offer a more systematic approach to everyday reasoning.
Like what kind of frameworks?
One is the pragmatic or dialogical approach. It sees arguments as speech acts within a specific dialogue or context.
So the rules depend on the conversation.
Kinda, yeah. The standards for a good argument depend on the goals of that dialogue. Douglas Walton, for instance, views dialogue like a game with rules and goals. Arguments are moves. Correct moves advance the dialogue. Fallacies violate the rules, which might differ for a debate versus a negotiation.
So it's not just about the logic inside the argument, but how it functions in the interaction.
Precisely. Another angle is the epistemic approach.
Epistemic meaning related to knowledge.
Exactly. This focuses on how arguments help us gain or justify knowledge. A good argument should move us from justified beliefs to other justified beliefs.
So arguments are tools for learning.
Right. Fallacies, from this view, are failures in that knowledge-gaining process. Like begging the question, it uses the conclusion as a premise, so it provides no new justification. Logical rules are seen as norms for achieving epistemic success or rationality. The Bayesian approach fits here too, seeing reasoning as updating probabilities, degrees of belief.
That's very practical, judging arguments by whether they actually help us know things better. Okay, logic clearly isn't just theory. Where does all this research get applied?
Oh, everywhere. Logic tools are used in ethics, computer science, linguistics. And conversely, logic itself is studied using tools from math and philosophy. Research looks at applying logic, but also at its own foundations, assumptions, and properties.
What are some of the big research areas now?
Well, there's the philosophy of logic and philosophical logic. Philosophy of logic asks fundamental questions. What is logic? What are its limits, its assumptions? Philosophical logic uses logical tools, often extended or deviant logics, to tackle philosophical problems in metaphysics, ethics, epistemology.
Using logic to probe the big questions.
Exactly. Then there's metalogic.
Studying the logic systems themselves.
Yes. Investigating properties like provability, consistency, completeness, soundness, decidability. Can an algorithm decide truth? Expressive power. It uses mathematical methods to analyze the formal systems from the outside, looking at the relationship between syntax, rules, and semantics, meaning
like quality control for logical systems.
You could say that. Then there's mathematical logic, sometimes used interchangeably with formal logic, but more specifically, it's logic studied within mathematics.
How so?
It includes areas like model theory, interpretations of formal languages, proof theory, structure of proofs, set theory, foundations of math, and computability theory. What can algorithms compute? It explores math's foundations, leading to things like logicism, the attempt to base all math on logic, which hits snags like Russell's paradox and Gödel's theorems.
Right, the limits of formal systems.
Exactly. Set theory is still hugely important. Computability theory looks at algorithms, Turing machines, the limits of computation.
Which connects to computers.
Directly. That brings us to computational logic. It's the intersection of logic and computer science.
Building logic into machines.
Essentially, yes.
Yeah.
Implementing logical reasoning on computers.
Yeah.
Think automatic theorem provers, logic programming languages like Prolog. And conversely, logic is fundamental to computers. Shannon showed Boolean logic could model electrical circuits, the basis of digital computing, logic gates.
Wow, from abstract ideas to the chips in our phone.
It's a direct line. Then there's formal semantics of natural language.
Using logic to understand everyday language.
Yes, it's a mix of logic, linguistics, philosophy of language. It uses formal tools, often from model theory, to analyze meaning, usually linking it to truth conditions. It relies heavily on the principle of compositionality, meaning comes from parts and how they combine.
Trying to bring logical precision to messy human language.
That's the goal. Finally, there's the epistemology of logic.
How do we know logic is right?
Basically, yes. How do we justify rules like modus ponens? How do we know logical truths are true? Is it a priori knowledge, through reason alone, through understanding language conventions? Or, as some argue now, does it have an empirical basis?
Empirical, based on the world.
Some argue logical laws might reflect deep regularities in the universe, potentially even challengeable by science, like some interpretations of quantum mechanics questioning classical rules.
So even the certainty of logic itself is debated. Okay, let's wrap up with a quick look back. Where did all this start historically? It wasn't all invented recently, right?
Not at all. Logic developed independently in several ancient cultures. In the West, Aristotle is the giant. 4th century BCE Greece. Term logic, syllogisms.
A foundation for centuries.
Absolutely. He also touched on hypothetical reasoning, modal logic, induction. Hugely influential until the 19th century.
What about elsewhere?
In the Islamic Golden Age, logicians like Ibn Sina, Avicenna, were crucial. Avicennian logic built on Aristotle, but added much, influencing medieval Europe. He worked on propositional calculus, temporal modal logic, inductive methods. Fakhr al-Din al-Razi also critiqued Aristotle and developed inductive logic.
So important developments in the Islamic world, too.
Definitely. Medieval Europe then saw translations of Aristotle influenced by Islamic thinkers, people like Boethius, William of Ockham. And in China, schools like the Mohists and the School of Names debated language and reasoning. In India, Nyaya, Buddhist, and Jain traditions developed sophisticated logic tied to epistemology inference as a source of knowledge. The Navya school had ideas remarkably similar to modern concepts.
It really is a global human endeavor trying to understand reasoning.
It is. The big shift to modern symbolic logic happened mid-19th century, spurred by questions about math's foundations. Frege's Begriffsschrift in 1879 is often seen as the turning point, though Leibniz, Boole, Peirce laid groundwork. Then Whitehead and Russell's Principia Mathematica in the early 20th century aimed to derive math from logic.
Introducing functions, quantifiers.
Yes, within rigorous formal languages. First-order logic became the standard, enabling formal math, set theory, model theory, modern mathematical logic.
A real revolution in precision and power.
Absolutely. So we've covered a huge amount today. We started with what logic is the study of correct reasoning. We contrasted formal and informal approaches.
Right, the symbolic versus the everyday.
We looked at core concepts, premises, conclusions, truth, logical truth, truth tables. We distinguished deductive certainty from amplitude probability.
And talked about fallacies when reasoning goes wrong.
Exactly. We surveyed different systems, Aristotelian, classical, the extensions like modal logic, challenges from deviant logics, and even systematic approaches to informal logic.
Plus all the areas where logic is researched and applied today in its long history.
It's truly remarkable, isn't it?
Gah.
Logic isn't just some dusky academic topic. It's the bedrock of clear thinking, impacting almost everything we do.
And hopefully, for you listening, this deep dive has given you that clearer, more insightful grasp of the core ideas without getting bogged down. That was our goal anyway.
To provide that shortcut to understanding.
So here's a final thought to chew on. How can really understanding the structure of arguments, whether they look formal or just pop up in conversation, empower you? How can it make you a sharper consumer of information, a clearer communicator? Think about the arguments you run into every day: news, social media, work, family. How could applying some of these logical principles help you evaluate them better or build stronger arguments yourself?
Maybe something specific caught your ear today: fallacies, formal systems, maybe those weird deviant logics.
If so, we definitely encourage you to explore further. There's always more to learn. Thanks for taking this deep dive with us today.